Okay, good morning. So I think there are many sessions that we promised to solve the problems from the previous sessions, but we haven't got time to do it. I think that's good if we actually relax a little bit at this point and try to go back and solve those problems which was left. But unfortunately, I do not have the complete list of the problems, but let me just see what we can do. One of the problems that I want, I don't know if you remember or not, the problem was this. So you have a straight line, yes? So let me call it, I don't know what I called it at that time, but let me just call it L. And then I give you 2 points on one side of L. Let me call them A and B. It's an important problem. I want you to, after learning that, I want you to have it in your memory if you're going to solve hard problems in geometry. I ask you to locate a point on the line, call it M, so that when I join M to A, when I join M to B, and I calculate the sum of these lengths, this becomes a minimum. This becomes minimum, actually. So what I mean, for example, if I choose this point here, M, and I can join this to this, and I join this to this, I don't know, it seems that the sum of the blue ones are longer than the sum of these black ones, but there is no guarantee yet that the sum of these black ones is the lowest value. Yes? So we want to locate a point in some way, call it M, so that when I join M to A and to B, the sum of these two becomes as low as possible. But that was one of the problems. I don't know how many of you have thought about it. It's really important to think about the problems, because when I present a solution, of course, you will understand it definitely. But the point of these lessons are actually to prepare yourself to be able to solve a problem that you haven't already seen. And that is really interesting, that how many new problems people can design. Because the people who are working in this field, they're actually very eager to see all the problems and try to solve them. But whatever they do, they cannot cover all the problems. So, do you have any idea how to do that? This problem would be very simple if I have given you A and B on different sides of the line. Hopefully in that case you can immediately answer me yes. So assume that I gave you this line L as before, and I give you this A, but instead of putting B on the same side of A, I put B here. And I ask you the same question. I ask you, locate a point on L so that when I join it to A and join it to B and add them up, it becomes as low as possible. The answer to this case is more or less trivial. What is that?
The line passing through A and B?
Yes. So if I join these two, yes, it's because one of them is on one side, the other one is the other side, definitely it will intersect this line at a point M. Yes? Now the claim is that this is the point that I am looking for in this scenario. But we have to prove it, because that's just a claim for the time being. How can I prove that this is really the case? How can I prove that this point makes this sum minimum? So if I want to prove my claim, I have to show that for this particular point, MA plus MB is minimum. So how should I prove it?
This is probably not enough to prove it, but the shortest path between 2 points will always be a straight line.
Mm-hmm.
And since we want to make our path as short as possible, M should lie on the.
That's completely true. But if you want to put it in a firmer ground, how do you do that? When I say that M is the minimizer, it means that if you choose any other point and do the same thing, it becomes longer than the previous case. This is the strategy if you want to show something is minimum. Yes? So what I do, I would say that, okay, if you don't believe in me that MA plus MA, M is the answer, let us choose any other point that you like except for M. Let me call it N. And I do the same thing, yes? I join N to A, and I join N to B, yes? And then what happens, I want to show that NA plus NB is longer than MA plus MB. But that is now clear, yes? Because in this triangle, I have the triangle inequality. So I know that NA plus NB is longer than AB. But what is AB? AB is just MA plus MB. Yes. So it means that if I find this point, any other point makes this sum bigger than the sum corresponding to M. So this means that M is the minimizer. Yes? Is that clear? So the line of argument should be reasonable for you. If not, please ask me a question. So this is more or less trivial. If I have one on one side and B on the other side. But now we want to do the same problem, but A and B lie on the same side, either on up top or on the bottom, doesn't matter. We want to do the problem for this case.
Great.
Okay, so let me just draw the picture again. And then, so this problem has two parts. First, you need to...
What was triangle inequality again?
The triangle inequality is the sum of the sides is longer than the third side.
Oh, is that something you said? Okay.
Yeah. So, okay, now let me just draw the picture again here for you. So we have here line L, and then here I have point A. Of course, when I say I have line L, it continues forever, and then I have B. Okay, the question is again, locate a point on L so that makes this sum MA plus MB minimum. That problem is not that trivial as before. So, do you have any suggestions? Let us wait.
Vänta, nu ska jag visa att...
If you want, I can give you a little bit of time to think, but I really recommend you to think about the problems after the video is published, because the whole point of what I am teaching you is to be able to solve a problem. Of course, you can sit and listen and enjoy if you like mathematics. They are really, really nice problems. But the point is that so using those information that I deliver here, you should be able to solve hard problems, yes? Okay, so I will pause the recording for a while so that you can think about this problem. And after that, I want you to send it to your memory. This is a very standard problem. So one more point. So you need to tell me how to find M, and then you have to defend why your method actually gives me the minimum. So this problem has two parts. First, think about a way to tell me how to find M on L, and then tell me why the method that you present works. Okay, do you have any ideas now? Yes, yeah.
I have an idea, but I'm not sure if it helps.
Yeah.
So I joined A and B, and then the midpoint, I drew a perpendicular line.
Okay, so let us see. So you are saying that you join these two, and then you find the midpoint, and you drop in the perpendicular line.
No, perpendicular to AB.
Ah, to AB. Okay, so you mean that a perpendicular bisector?
Mm-hmm.
Yes?
Yeah.
Okay, and then you are claiming this is the M?
Yeah, because then if that point is M, then MA is equal to MB, but I'm not sure if that means that it's the smallest distance.
Okay, that's important. So that is important. So you have produced a method that generates a point on this line, But what we want to prove is that MA plus MB is the lowest possible. Yes. I don't know if you can defend it yourself. That's your method, you have to defend it. If you can't defend it, then we have to admit that this is a correct solution. Any other ideas? Yes?
What I did, I dropped a perpendicular line from A down to.
So let me just clean this. So what you are saying now, if I have this point A here,
Yes.
and then if I have the point B here,
Yes.
okay, what I should do?
I drew a perpendicular line to L passing through A.
Okay, so you drop a line
Yes.
from A
Yes.
to L perpendicular.
No, passing through L.
So
It's supposed to go down below L.
Ah, okay, so how much?
Around the length of A of this line, of the first line.
No, that is so you mean okay?
Forever.
forever. Okay.
And then I drew a circle with. Okay, so the intersection point of this.
Yeah.
Let's call it
H.
H. And I drew a circle with H as its center. That passes through A.
Yes.
So this circle, and then this. And I drew the intersection point, that, and call it whatever. And then I joined K and B. And then
You are claiming this is your point.
Yes.
Okay. First of all, that's completely correct. That is the point. But the point is that you don't need to mess it up so
No,
much.
I think I did it a bit more.
You don't need to say circles and things. Of
Yeah.
course,
But
at that level, you really don't need to motivate the people how to do it.
No.
So you can say that you drop a line, perpendicular line to L, and extend H to its own length.
Yeah.
That's enough.
Yeah.
But this is the method for you
Yeah.
to do that. So you really don't need. So if you don't mind, let me just clean this. But your method is completely correct. The only thing left is that you have to defend yourself. So what we have this point here A, and this point here B, and then here we have this line L. And then what he said that we drop a perpendicular line from A to this line, okay, and then extend this line segment to its own length from the other side, so that I get a point, I call it A prime, for example. So based on my construction, or Oscar's construction, these two are the same. Yes? And then what he's saying is that you take your straight edge, or just the ruler without calibration, and just join these two. Yes? And if you do that, it will intersect the line at a point. He is claiming that this point is your minimizer. Yes? So in principle, you see, actually Oscar reduced this problem to this old problem somehow. That these two lines, these are on the different sides, yes? So what happens is that what we are supposed to prove, we are supposed to prove that if I join M to A, and if I join M to B, which is already done, we want to show that for this particular point, MA plus MB is the minimum. In other words, M is your minimizer. So we have to defend that. So how should we defend that? The strategy is more or less the same. You should say that if you choose any other point, you prove that the new sum is larger than this sum. If you can prove it, then we are done. Is that clear? So how should I do that? You would say that, okay, if you believe in me, we are friends, no argues, but not, let us see. If you say this is not the minimizer, then something else is the minimizer. So let us, for example, take this one and call it n. Then I want to show that no, n is not actually the minimizer. How should I prove this? I would say that, okay, let us join these 2 points to n. Yes. Now, we show that the new sum is definitely larger than the previous sum. Yes? So how can I prove this? So the claim is this. This is my claim now. I have to defend that. That NA plus NB is larger than what Oscar actually proposed. MA plus MB. If I can show this, and my argument is really independent of the location of n, you have to convince yourself of that as well, then we are done. Okay? So now we want to show that NA plus MB is larger than MA plus MB. So what is your suggestion? Yes?
If you join A prime to N.
Here to here?
Yeah.
Okay, so let me change the color. Whenever you join something in the exam, you have to write it down, okay? So we are talking it orally, but you have to put it in the written form. So you say that now, to defend myself, I join A prime to N. Yes?
And we already proved that if in the case of B and A prime, it's obvious that the point N would not, that this distance is longer than if you were to choose the point M.
Mm-hmm.
But we also see here that if you call H and A
No,
prime,
make it simple.
Okay.
So don't go back here.
Well,
So what you are saying is correct. So first you need to convince yourself NA and NA prime have the same length.
Yes.
Yes? Why? So this is something that you should be able to show it for me. Why NA and NA prime have the same length?
they're congruent.
Okay, so this is, you see that we are using the congruency of triangles. Why? This length is equal to this length by construction. HN and HN are common to this top triangle and this bottom triangle. Do you agree? HN is the common. And then this is 90, this is also 90. So I would say that if you want to write everything in detail, so you would say that AH is equal to HA prime. You would say that, let me call it angle H1, angle H2. Angle H1 is equal to angle H2 is equal to 90 degrees. And then you would say that HN is also equal to HN. Then based on what congruency SAS congruency axiom, then the triangle AHN is congruent to the triangle A prime HN. Do you agree? Because of that, and then if they are the same, I can also conclude that the length NA is equal to length NA prime. Yes? So, if I go back here, NA, therefore, NA plus NB can be written in this form. Instead of NA, now I can put NA prime. So this becomes NA prime plus NB. Yes? But NA prime plus NB, consider this triangle. Yes? So these are the sum of two sides. It is definitely longer than the other side. Yes? So the triangle inequality tells me that this is definitely longer than A prime B. But A prime B can be decomposed into two parts. A prime B can be written as MA prime plus MB. Yes? But then, I hope that you can immediately see that MA prime is also equal to MA, based on the same arguments. But of course, you have to argue that. This length is equal to that length. HM is in common. These two angles are the same. So these two triangles are congruent. So MA prime is indeed equal to MA. So instead of MA prime, now I can replace it with MA. Yes? And now we are done. Look, this expression is equal to this expression. This is greater than this, but all of them are equal. So this means that what you have here is greater than what you have here. Is that understandable? When you look at the picture in the final form, it seems complicated, but if you feel the logic, it was completely clear that we have to go through this way. So is that clear for everyone? Do you have any questions? But there is one part missing in principle. Before doing that, I have to write it down that MA prime is also equal to MA. So I have to write congruency of these two as well, and then use both of them. Yes?
We can't just say that, like, by using the same argument, we can also prove that HM is congruent to
Yeah, I think this is so simple that probably they don't deduct any
Problem
points
is
from
prove
you.
at any point on the line L. Will
But I would I will prefer not to risk something else. I don't know. But in principle, yeah, you can say that. Is that clear? Okay. So from now on, you know how to find a minimizer. If they are on different sides, just join them. If they are on the same side, reflect one of them about this line, or find a mirror image of that point, and then join these two. This will give you the same point. But do you think this will be affected? In principle, I should be able to do it from the other. So Oscar started from A. But do you think I can start the process on B? In principle, the answer should be the same or not.
Yes.
Because yeah, the minimizer, I hope that you agree with me, the minimizer is one unique point. So in principle, you should be also convince yourself you can go on and practice. If I drop a line from here and extend it to its own length from this side and join it to this, definitely it will intersect exactly at M. Yes?
I mean, yeah, these A and B are just labels we've arbitrarily chosen. We could just as well decide that.
Yeah,
They're called
because if it
BA.
was not like this, then
And
we will really in trouble. So it means that nature somehow prioritized one of them over the other. Yes, but it doesn't. Okay, so one more thing that I want you to know is that, what can you say about these two angles? If M is the minimizer, so you see N is not the minimizer, if I consider this angle and that angle, even in my picture, it's clear they are not the same. Yes? But now, if M is the minimizer, what do you say about this angle and that angle? For the case that M is minimizer, they are equal. Why? Because we know that this triangle is congruent to this triangle, so this one and that one would be the same. But on the other hand, this one and this one are opposite or vertical angles. So this means that these two should be the same. Okay. Yeah, so that is also good to know. So if you have a minimizer, these two angles should be the same. Okay, so this was one of the problems that we had before. I don't know, there was also another problem that we had. It's good to remember this. And then we also had another problem. So let me just draw it here. I hope that I can. Do you have the letters that I used for that problem? Let me see if I have it here somewhere. This square that you told me, Ross, you solved the problem. So here we have this square. So I have it here with me. So we have A, B, C, and D. This is given to be a square. And I told you that just pick a random point on the line segment DC, for example. Just let me call this E. It's a random point there. And then what happens is I join A to E, and then I draw the angle bisector of this new angle which is generated now. So I will drop angle bisector. This angle bisector will go and intersect this at a point which at that point I called it F. So what I told you that this angle alpha, whatever it is, this one is also alpha. So I am just drawing the angle bisector here. It will go and intersect somewhere here, and then we were supposed to prove, and then unfortunately I don't remember which one was which. Do you remember? We want to prove that I think BF plus BDE is AE, yes? So the point is that we want to prove that DE plus BF is equal to AE. That's an interesting problem, I would say. You see, you just pick a random point, and when you join, you have an angle here, you bisect it, it will go and intersect this line, take B to F, and add it from D to E. Then, interestingly, if you add these two, it becomes the length of AE, regardless of the location of E that you choose it. Okay? So, any ideas?
Ja, det var så där vi gjorde.
Man måste bara markera upp den där och den där. Egentligen. Ja, det är egentligen bara de här två och den där.
So if I want to motivate you, so let me tell you, so DE plus BF, of course geometry is so diverse that we have different diversity of problems, but here BF is on this line, but unfortunately DE is on this line and AE is completely different. So if I want to prove the sum of these two, because the sum of two line segments are easy to know about if they are on one after the other, yes? If this is A, this is B, and this is C, if I ask you what is AB plus BC, you can immediately answer. This becomes AC. Yes, this is trivial. But the hard part of this is because one DE is here, the one line segment is here, the other line segment is not on the direction of DE or on the line of DE, it's somewhere else. So, can we somehow construct this to be able to solve this? Because this is probably the standard way of thinking. So you need to look for it. Yes, Rasmus?
If we like focus on the triangle ABF.
BF, yes.
We can take that triangle and rotate it and place it beside AD so that the line AB now lies on AD.
Okay, so what you mean essentially, so if you don't mind, let me rephrase it. That's exactly what you said, but I would say that I will extend this, and then so that, until which point, so that this length and that length become equal.
Yeah, I guess so.
So, for example, let me call it H, for example. So is that clear? Now that's by construction. So you have to explain it in words. You should say that, for example, I extend line segment DC from D side to a point H so that DH becomes equal to BF. And for not being confused yourself, let us equip them with two dashes here. So that is by construction. So let me write it down. By my construction, or what Rasmus actually said, these two are the same.
Yeah.
Okay? And then you would say probably join H to A.
Yeah.
So let me just describe what was the motivation. The motivation was, if I ask you, can you say something for DE plus BF on this new picture, the answer is yes. Because DE plus BF now becomes DE plus DH. And then everyone knows that this is HE.
Yeah.
Yes? So that is exactly the motivation, because the important point in these lessons is not just learning the new method. So you need to have some ideas so that you can have it in your memory, being able to apply it for the next problem. Okay, and then
So then we can. So now we can say if we focus on the triangle DAE and
DAE,
DAE.
yes.
Yeah, that triangle. And we look at the angle at A
Yes.
for that triangle. That should be 90 minus 2
Alpha.
alpha.
Everyone agrees, yes? This angle is
Because
90
it's-
minus 2 alpha. Why? Because the whole angle of the square is 90, 2 alpha of that is gone.
Yeah.
So what is left is 90 minus 2 alpha. Okay?
And then let's see. Yeah, and if we look at
Can you tell me what is your goal? Because people will understand that better. So
Yeah.
what is your final goal?
so my final goal is to say that this triangle HAE is
HAE,
an isosceles triangle
isosceles triangle.
where
With apex. By the way, this is called apex.
apex. Okay.
Yeah, apex or probably apex. I
Yeah.
have to check my pronunciation. So this E, so you show, this is because if he can succeed to do that, then it means that AE is equal to EH, but we already realized that EH is the sum of these two line segments. So then we are done.
Yeah.
That's the goal. Okay? And then for making a triangle isosceles, it's a good idea to work with the angles.
Yeah.
So this is the, so then you start playing around with the angles to see what happens. So the final goal would be to show this angle is equal to this angle. If I can show these two angles are the same, I am done.
Yeah. So if we check like that angle H in our original triangle ABF, let's see, yeah, that's the angle at F.
Yeah, so that is if this is beta, you are claiming that is also
Yeah.
beta. And that's by construction clear, okay? Rasmus talked about rotation. Of course, if you rotate, everything will remain the same. But the way that I explained, you should say this one is equal to that one. This one is equal to that one. Yes? And this angle 90 is equal to that 90. So it becomes SAS axiom.
Yeah.
Yes? So these two triangles are congruent. So if this angle is beta, this angle is also beta.
Yeah.
Yes.
And that angle beta is equal to 90 minus alpha because it's a right angle triangle and the other angle of ABF is alpha.
Yes. So you see beta plus alpha is 90. Yes? So beta is 90 minus alpha. Yes?
Yeah.
And then that's also the same thing. What is this angle?
It's alpha.
Because this triangle is congruent to this triangle. If that's alpha, that's also alpha. Yes? And then we are done. Because this part is alpha. This part is 90 minus 2 alpha. If I add them, it becomes 90 minus alpha. So this triangle, this angle is 90 minus alpha. This angle is also 90 minus alpha. So this triangle is an isosceles triangle. So it means AE is equal to HE. But HE can be written as HD plus DE. But HD is equal to BF plus DE and weird. Yes. So that was also nice. But the lesson is important. So you see this trick you should have sometimes in mind, yes, by solving more problems. Thank you very much. That's completely correct. Is it clear? Yes? Yes? Yes or no?
No, I just came here, so
No, no worries. But this problem you were here. Do you have any questions regarding this?
no.
It's understandable.
Yeah.
Good. Okay. There was also another problem, if you remember. I gave you any triangle in principle, ABC, and then I told you that you make an isosceles triangle on this side with this vertex, and then you make another isosceles triangle on this side, exterior to the triangle on this side. Okay, so what does it mean? It means that, for example, of course it is a little bit hard, but not only isosceles triangle, we have to make it in a way that it works as I'm just explaining. So assume that this is equal to that. So I construct an isosceles triangle. So this is very hard to draw the shape in a correct way, but, and I don't know, that's also a very challenging problem to make it right. For example, by GeoGebra or whatever. And then I make this one equal to that one. So what I have done, I made an isosceles triangle on this side here, and an isosceles triangle on this side here. How many triangles I can construct? How many isosceles triangles I can construct here and there? Infinitely many here, infinitely many there, by changing this angle. But the problem tells you that no. Choose those ones that also have another condition, and that condition is this. So it is named in the problem. If I remember, I call this D, I call this E. And now another constraint among all those infinitely many triangles that we can construct on these two sides, choose the ones that satisfy this condition as well. So if I join D, oh sorry, okay, so I join D to E. But the point is that this angle DAE is also equal to B plus C. This is part of your assumption. Okay? So this is a little bit hard. Even I don't know how to construct this setup. I think that's also a challenging problem to see. At least we can draw these isosceles triangles in a way so that when I add these three angles, DAE, it becomes the sum of B and C. Okay, so for the time being, we are not concerned about construction, but I would say that this is not that trivial, how to construct this setup. Okay, but assume that this is the case. If this is the case, based on this fact, we want to show that if I find the median means I find the midpoint and join A to M, we want to prove that under these conditions that I told you, the length of DE is 2 times larger than this median. Yes? So if we can set up this construct with this condition, then we want to show that in that particular case, the length of DE is 2 times larger than the length of this median. So this is also a nice problem. So because the figure is unnecessarily complicated, but the argument, if you find the right argument, the problem is actually very simple. And by the way, what I want you to learn is how to think. You see, this is somehow a guide for you, because it is telling you that you are supposed to show DE is 2 times larger than AM. If you remember when I was teaching, I told you whenever it comes to median, think about one thing that might be useful. What was that? To extend the median to its own length. And that is very relevant. It seems very relevant here, because if I extend this to its length, what I get is 2 times AM. And then what I have DE is that. So if I can prove the new line is equal to this, I am done. I'm not saying that this definitely will work, but the point is that you have to have some anchors in your mind, so you have some patterns in your mind to be able to compare what you have with what you had, yes? So let us just do that. Hopefully it will work. So, but you need to write it down in the paper. I won't just describe it orally here for you, but in a real exam you have to write it down. So what we do, we extend line segment AM from M side to its own length. Yes? So that we come to a point, let me call it A prime. I hope that you agree with me. A prime is indeed 2AM because of my construction. So my point will be, is it possible for me to show that AA prime is equal to DE. Yes? The only tools that you have right now is congruency of triangles. That's more important. Now, can you continue? I think you solved the problem, yes?
Okay, so after you do this, you connect A prime to B and C.
To both of them?
Yeah.
Do you need to both of them, or one of them
Well,
is
I
enough?
need to prove that to prove that angle is BC, as B plus C. Well, either of these.
So if you don't mind, I think one of them is enough.
Is it? Because I think.
So let us, for example, let us join. So you need to write it down again, and then we join A prime to say B.
Okay. Yeah.
Yes.
Yes.
So I extend this. So let me see what I have at my disposal. I know that this blue dotted line in size is equal to this orange line. This we know. Okay, and then hopefully you realize what to do. Your goal is to show that this length is equal to this length.
Yes.
If you want to use, I'm not saying that this is all the time. If you want to use congruency of triangles, you have to have a rough guess about which triangles to compare. So which triangles do you think it would be good if I can compare? And there is a chance for it, because of course the picture is very poor. Might be you cannot really see that. But what do you think would be a good candidate for comparing triangles? Which triangles are good candidates? Can you just name them?
BA prime and BD
BA prime,
and AD.
BAA prime you mean?
A
yes?
prime.
BAA prime and
AED.
triangle AED. Okay. Okay. So this is good candidate. So what Oscar is mentioning, he's comparing. He's trying to compare this triangle with this triangle. I have to go inside here as well. I hope that you are not confused. These two triangles should be compared. Okay?
Yeah, we only did need one to connect one.
Yeah, then one is enough. Do you agree?
Uh,
Okay, so now what do you say? So these two triangles are congruent, but before doing that, you need something to prove.
Yes.
What is that?
Well, first of all, I want to prove that this angle is that angle is the same as
C.
Right.
Yes, we want to prove that this angle, by this construction, and this angle are the same.
Yes.
So to do that, I need to consider congruency of two other triangles, because all of them, by the way, are standard ones. So you know that this triangle that here is congruent with this triangle there.
Yeah.
Why? We have to write it down. So why? Because you told me that M is the midpoint. So I can say that BM is equal to MC, yes? And I myself extend it to the same length, so I would say that MA prime is equal to MA. Do you agree? MA prime and MA are the same size because of my construction. But then, so that's not a good idea. So let me write MA prime here and MA here to be more organized, yes? And then this angle that you see here, I call it M1, and this angle that you see here, let me call this one M2 and this one M1. So then this means that angle M1 is equal to angle M2 because they are vertical angles. So this means that based on SAS axiom, these two triangles are congruent. So you have to write it down. So I would say MAC is congruent to MBA prime. Yes? If these two triangles are congruent, then it means that this angle that I am looking for, so if you don't mind, let me call it alpha, then this means that this angle should be equal to this corresponding angle. Yes? So that is what we have. Okay, now let us go back to the original comparison here. So what can I do? I can say that this AB is AB from this triangle is equal to AD from this triangle. Why? Because you see it's still the dashes are there, yes? So AB and AD are the same because this triangle was an isosceles triangle. And then we also know that, by the way, that is not enough yet, because this triangle is congruent to this triangle. One consequence was that. Another consequence was BA prime is equal to AC. And AC itself is equal to AE. Yes? So what can I write? I can write that BA prime, let me write it here, BA prime is equal to AE. And now, look here. This angle is given to be B plus C from the beginning. Yes? And now this angle, what is the size of this angle now? This is already B. This is alpha, but we learned that alpha and C are the same. So this angle is also B plus C. Yes? So this means that these two angles are the same. So what I would write that angle AB A prime is equal to angle DAE. Again, based on SAS congruency axiom, I can conclude that the triangle ABA prime is congruent to triangle AB, so ADE. And if they are the same, so this means that AA prime is equal to AE, is equal to DE, I'm sorry. AA prime is equal to D. And AA prime is 2 times of AM. So this becomes 2 times AM is DE. And then we realize that they are the same. Okay, so of course this problem itself is beautiful. You can enjoy that. But the point is that you have to take lessons. If you solve it, that's good. But if you couldn't solve it, you need to take lessons for your future. Why I couldn't solve it? This is not something that I can teach you. You need to find your own way to say that, okay, why I could not solve this problem? What should I do for my brain to be able to see the pattern next time? And that's the only thing we can do, yes? So that's also one problem which was left. But the most interesting problem probably is the one that we talked about last time. And I actually I want to follow your method, Oscar. So, okay. But if I cannot, you can help me. But let me explain it myself, okay? Because that's a hard problem. I want to make sure that everyone understands that. But if I forgot the details, you can fill the blanks. Yes. So this is a really nice problem, and you might see that how human can be creative, because at least this problem is given to us. We know that there is a solution to the problem. But now you assume that you want to design the problem yourself. I don't know. So you need to understand this is not easy at all. So this problem I want to describe here. So before that, let me just remind you, if you have forgotten, if I have a triangle, any triangle, ABC, we learned last time, and that was an extremely important theorem, that if I draw the angle bisector of this angle, making these two angles the same, and if I draw the angle bisector of this one, making these two the same, and draw the third one, it's extremely nice and important property that it doesn't just pass everywhere, it just passes exactly through this intersection point. And the terminology we used is that the interior angle bisectors are concurrent. Concurrent, yes. Yes. So this that point has a name in geometry, and that is called in-center. And letter I is reserved for that. So, this is the in-center. So you know what is in-center. Now, the problem is, you have a function. Now I am just phrasing the problem again. You have a function, its name is f, but what is its property? First of all, when I talk about a function, you should expect immediately two things. The function takes an input and gives you an output, if a function is once in a single variable function. So this function, but what you can put in or what you can put out, it's completely generic. You can put numbers in, get numbers back. For example, if I have a function of this form, this tells me that if you put a number in, it squares the number and gives you back a number. Yes, that's a function from numbers to numbers. Yes? But this is not a necessity. You can have a function of any kind of objects, in principle, to any kind of objects. Yes? So now this function in this problem that we were interested in is a function that takes in a point on the plane. So assume that I am working on this whiteboard plane. This plane continues forever from all those directions. This function is a function so that the plane is its domain. Yes? It takes inputs from the domain, and the domains are points. So let me call it a point M. Okay? But this function is assigning a number to each point. So it gives a number. What type of number? A real number. So this is a function which is called a real valued function. What does it mean? It means that the output is a real number. So that's a terminology I want you to learn. When I say that I have a real valued function, it means that the output of my function is a real number. But in this problem that I want to set up, the input of my function is a point on the plane. If I give what I don't know, because you know that function should do something for us. We don't know what this function is doing. We just know that this function takes a point on the plane, gives you a number. According to which rule, it's a mystery. We don't know. Yes? That's the function. But we know something about this function. We know that if I choose 3 points, say A, B, and C, okay? And determine f of A. F of A is a number based on my definition. And then do the same thing for B. And then do the same thing for C. And add them up and then divide by 3. Can I divide by 3? Yes, because f of A, f of B, and f of 3 are numbers. It's real value. When I add them, it becomes a number, so I'm allowed to divide a number by 3, so it becomes a number. And so this function is a mysterious function, but this gives me the value of function at the in-center of that triangle. So it's a very, very strange property, yes? So we know that if you give me a triple of points on the plane so that they make a triangle for me, if I calculate the value of my function here, here, and there, and then add them, divide by 3, it becomes the value of the function at the in-center I. So just let me repeat. What type of function is that? We don't know yet. We just know that this is valid. Not for this triangle. If I choose this triangle here, it will work. If I choose this triangle here, it will work. Yes. Now the point is that the claim of the problem is this. The claim of the problem is show that. So let me write. When I say claim, I don't need to write the sentence. F is a constant function. F is a constant function. What does it mean? It means it is a function it gives you always the same number for every point. Yes? So it tells you that if you agree that your function enjoys this property, then you have to admit that this function is a constant function. A constant function is a function gives you just one particular number regardless of which input you put in. That's called a constant function. For example, in math, normally we see, for example, f of x is equal to 5 is a constant function. Because it doesn't matter what you put in, the output is always 5. That's a constant function. And what that constant is, we don't know. We are just claiming it's a constant function. But that's actually a completely broad problem. Yes. Okay. This problem is really hard, I would say, and really beautiful. So that's, I want to follow me, just try to enjoy it, okay? So, I gave a hint to Oscar and Rasmus, and then they try to actually visualize it. But before that, if I want you to understand, how can I prove this claim? I want to prove that f is a constant function. What should be my strategy? How can I prove a function is constant? Yes?
Whatever you put in, the answer will be the same.
Okay, so what in practice what should I do? I would say that let A and B be arbitrary points on the plane. We show that. Okay, can you Hafsha mention what should I show? We show that what?
That they are like a fixed point.
No, better than that. I want you to write equality. We show that. You said that they said the right thing, but I want you to rephrase it.
A is equal to f of a.
No, be careful. Think about it. Everyone, you can contribute. What Hafsha said is completely correct, but you need to translate it into mathematical notations. So you said what? You said that whatever you put in, you get the same number. So now I have put A and B in. Putting them in means f of A and f of B are the same. That's the meaning of the constant function. So it means that, so what you said is exactly, if you want to translate it more mathematically, it means this. It means that whatever I choose for my inputs, A and B, f of A and f of B are the same. And because these argument, if I can succeed to argue for you, is an arbitrary pair of points, I can repeat the process for any other 2 points that you give me. And then it means that f of A is equal to f of B for any pair. And that means that function is constant. Yes? Is that clear for everyone? Yes or no?
Yes.
Okay. So the point is that you give me 2 points where, here, for example, I don't know which one you are suitable to. Yes, sir. You told me A, put A here, yes? I don't want to confuse you because I want to reproduce what your solution. So you give me f, A, and B somewhere on the plane, arbitrary, and then I want to show that it doesn't matter. F of A is equal to f of B. But what I have in my hand is just this assumption. It's a hard problem how to connect these 2 things together. Yes? Okay, now I gave them a hint. The hint is to construct a regular pentagon on this line segment, which is extremely extraordinary, yes? Why on earth I should think about constructing a regular pentagon on the point. So don't get confused. I had these 2. My goal is to show f of A is equal to f of B, regardless of the location of A and B on the plane. Now, my way of thinking is to construct a regular pentagon on AB. What does it mean? It means that I just join them. This has a length. I don't know. I construct the pentagon here, yes? But regular one. So don't get confused. The goal is still the same. I want to show that f of A is equal to f of B, This is the method that I am introducing. So we construct a regular pentagon on A and B. That was the hint that I gave them. But after that, actually, they were trying to solve the problem, and actually they succeed. But if you don't mind, Oscar, so let me just name everything, okay? Okay, so these are my original points. Don't forget about them. But then let me call these points for simplicity of reference. So this is C, this is D, and this is E. Okay, okay. Now I am just following you. So you told me that after this, you make a star here inside, yes? So he constructed a star in this. No. Okay. So if you need to be imaginative here. So it's completely symmetric. I cannot draw it precisely on the board, but that is a star that we construct in. But you might say why this is relevant. You have to wait and see how Oscar actually solved the problem in this picture shape. Okay. Okay. So what we are supposed to do now? Can you tell me, Oscar? So if you don't mind, let me call these some A, B, C, D, E, F, G. I don't know. You don't need all of them, but let me write H, K, L. Okay. So okay. Now, if you want, you can tell me. So what should I do?
Okay, so the first thing you need to establish is that okay, so the goal is still to prove that A equals B.
Yes.
So what I did was
F of A is equal
f
to
of
yes.
A equals f of B. So what I did was that first of all I proved that the triangle ALD equals the triangle BGD.
ALD.
Yes.
This triangle. Okay.
Yeah.
What?
Its incenter is the same as BGD.
Okay. So you see, consider the triangle ALD and the triangle what?
BGD.
BGD. Okay? ALD is this triangle. It's probably not a good idea to highlight it that much. And then BGD. This is BGD. Yes? Okay. I want to skip the proof for this part. I think it's not hard. But what Oscar is actually asserting rightly, correctly, that the incenter of this triangle and the incenter of that triangle are the same. Yes? It is not that trivial. How should you convince yourself? You need to say that, okay, let us concentrate here on this triangle, this angle bisector, and this angle bisector, and this angle bisector will intersect at a point, I will call it I. This I is the incenter of this triangle, yes? If I can do that. And now what he claims is that if I do the same thing for BGD, this triangle, if I draw the angle bisector of this one, angle bisector of that one, angle bisector of this one, they will also go through I. Yes? It is not hard. The shape is so symmetric that you can convince yourself easily that is indeed the case. But that is what he's claiming. And if you don't mind, for not making the problem, the figure complex, let me just get rid of them. But hopefully you agree with Oscar and me that I center of these two triangles are the same. Yes? Everyone okay? Okay, and then if I ask you for these 3 points, if I ask you what is f of A plus f of L plus f of D divided by 3, you should be able to answer that. What is the answer to this? I want to make sure that everyone understands. So, this is this triangle ALD, this triangle, and that is the I center. F of A plus f of L plus f of D divided by 3 is equal to what? Yes?
F of I.
F of I. Because of what? Because of my assumption. This assumption tells me that whatever you choose for A, B, and C, and if this I is the I center of that triangle, this is valid. Okay, and then we also convinced ourselves that is the same thing for this triangle. So it means that f of B plus f of g plus f of d divided by 3 is equal to what? Someone else. What's the answer?
F of I.
F of I. But why? So you see, it was crucial for us to realize this I is the same I center for both of the triangles. That is crucial part. Yes? And of course, if this fraction is f of I, what is f of I don't know. And if this fraction is also f of I, then these two fractions has to be the same. Yes? So this means that whatever this number is, it's equal to f of I. Whatever this number is, it's equal to f of I. So this number and that number are equal. So if you don't mind, let me just be patient and write it. Yes, divided by 3 is equal to f of b plus f of g plus f of d, and then divided by 3. And then this 3 and that 3 are cancelled if I multiply by 3. And then you see that f of d appears on the left and on the right. So if I move f of d to the other side, it becomes negative, and these are also cancelled. Yes? So then, unfortunately, we are close, but it's not done. So what was the goal? Don't forget about your goal in hard problems. F of a should be equal to f of b. But we didn't succeed yet. We succeeded to show that f of a plus this f of L is equal to f of b plus f of g.
Yes.
Okay? So this I call it number 1.
Yes.
So that's a nice relation, even though it is not finished, because there is no reason that I can get rid of these two. Of course, the goal becomes clear. If I am supposed to show f of a is equal to f of b, if I can show f of L is equal to f of g, then I am done, because then this will be cancelled and f of a will be equal to f of b. Okay, but then, because my method was different a little bit, so now I need for help for Oscar, so to see that how is it working from here.
Okay, so now we'll use this relation we have again, because we can also prove that the 2 points we have, G and L, they are the incenters of triangles.
Okay, so you are focusing now on G,
Yes.
Sorry, on L and G.
Yes.
So you are claiming what?
Okay, so L is the incenter of the triangle BEC.
Yes, let us see everyone is convinced by that. So you see, so he is claiming that this L itself is the incenter of this triangle, BEC. BEC. So in order to show this claim is right, I have to convince myself that this angle and that angle are equal. Why? Because I want to show that this is angle bisector. But I want to skip these things because the beauty comes after that. So, and I don't think it is hard for yourself to convince them. So this angle and that angle are the same. By symmetry, you can immediately prove that. And these two angles are all the same. So this means that these two angle bisectors intersect at L, and I really don't care about the third one, because the third one, according to that theorem, should pass through that. That's it. So L is a I center for this one. Agree? And now, if L is the I center for BEC, anyone else, can you tell me what can I write now? Someone else, because I want to be happy that you're understanding. So now he proved that L is actually the I center of this triangle. So what can I write? Any volunteer? Don't disappoint me, please. You should say something. So after that, if no one comes up, anyone else from this group? So what can I write? L is the I center of this triangle. So what can I write? Yes?
FB plus FE.
Thank you. So let's just continue. FB plus
FE plus FC divided by 3 is equal to FL.
Exactly. Everyone happy? Because that's the same assumption. Okay? Okay. Now this is the case. Then, so you want to do the same thing for G now?
Yes.
Okay. But now someone else, can you see G is I center of which triangle now? Yes?
AEC.
AEC, yes? So G, for the same kind of reasoning, G is the I center of this triangle. So what can I write? I can write f of A plus f of E plus f of C divided by 3 is f of G. Agree? Yes? Is that understandable? Okay, so what we happen, now we want to, so what we do, we want to prove that these two are the same. So what you want to do, is there any better way to do that?
No, what I did is that I took your one over there on the bottom.
Okay, so you place these two in that relation, yes? If I remember.
I replaced f of
So
L.
yeah, I call this number 2, I call this number 3. So I go back to number 1. Instead of f of L, I put this fraction. Instead of f of g, I put this fraction. Yes? So let us just do that. So comparing number 1, number 2, and number 3, we conclude that f of a plus, instead of f of L, I am allowed to put this, f of b plus f of e plus f of c divided by 3 is equal to f of b plus f of g. F of g is this one. So this becomes f of a plus f of e plus f of c divided by 3. Yes? And then the rest of it is just algebra. So I want to get rid of fractions, so that's a good point to multiply everything by 3. When I multiply this by 3, it becomes 3f of a. I multiply this by 3, this becomes f of b plus f of e plus f of c. And then on the right-hand side, I multiply this by 3, because if I multiply the left-hand side by 3 to keep the equality, I have to multiply the right-hand side as well. Then it becomes f of a plus f of e plus f of c. Yes? And now, just simple algebra. For example, I keep f of a, 3f of a here. I move one of them to the left. It becomes negative f of a, 3f of a, it becomes 2f of a. Yes? But f of e, whatever it is, it's cancelled. And f of c, whatever it is cancelled. Yes? And then I move f of b to the other side. I have 3f of b there, so it becomes 2f of b. And then finally I divide by 2, and I got it. F of a is equal to f of b. And what was the goal? To show that f of a is equal to f of b. It's no doubt, it's an extremely beautiful problem. You know? And now you need, I don't know how we can take lessons from this problem, but that is very close in nature to the problems that you're supposed to crack in a Olympiad test. Yes? So this kind of, so you have to be very creative. Of course, some problem, so you need to go, so the only hard part, of course these are also hard, but might be the hard part is to construct the right shape. Yes? And when I check the author's solution for that, one of them is based on Pentagon, but a little bit differently. That author was just drawing, continuing these sides, and then concentrating. The strategy is the same, concentrating on this triangle and that triangle. Algebraically it becomes easier, but I intentionally followed Oscar's method because when we were discussing together, we didn't find a way out of this method, but he were able to do it. So, and then another method is based on hexagons. Might be I can just give you the solution so that you can read and understand. But I would say it's extremely beautiful. So when you want to prove that a and b or f of a is equal to f of b, then suddenly you need to imagine that I have to make a pentagon out of it. Or in the other solution that I saw by author, you have to make it some kind of a very particular hexagon out of that. Yes, but that is really extraordinary. Yes, it's really counterintuitive. Why I should do this? But now, yeah, I think this is the most beautiful problem that we face during these lessons. Okay, so that's I would say it's extremely hard. Okay, so is that understandable? Okay, is there any other problem that I can give you one problem here? We have a little bit of time. This problem is not hard. I'm sure that there are some problems that we haven't finished, but might be if you go back and see the lecture notes, and then you can come back to me and try to solve that problem. Okay, so what I see is this problem. And by the way, let me also see the pronunciation of this apex or apex. Just learn it right now. Yeah, this Webster dictionary is probably the best for scientific purposes. And that's free, good. Apex, so that your pronunciation is correct. So that's apex, not apex, okay? So apex is, so if you have an isosceles triangle, this one is called apex. Yes? And thank you for correcting me, by the way. Otherwise, I would continue saying apex. Okay. So this, I have any triangle that you like. I think drawing these pictures are hard. By the way, that's also a nice problem. It's still in my mind. How can I construct this? It's not easy, I think. You can also think about that problem. So, but this one, I have a triangle, any type of triangle that you like. I start making equilateral triangles on the sides. Okay, so there are no options. Equilateral triangles are unique. Yes? So how should I do that? I make an equilateral triangle. It's hard to draw. It's perfectly fine. But so assume that, yeah. Very, very bad. Okay, so let me call this one, I don't know, C prime. Opposite to this, I call it C prime. So what I mean this one and that one and that one, I try to make them the same size. It's equilateral triangle. I do the same thing on this side. And I call this B prime, opposite to B. And I do once more here. I don't know if they are on the same side or not, but don't worry about it. We don't have any problems here. So this is so what I have this one and that one and that one are equal. I have this one and that one are equal. And then, according to the problem I saw yesterday, so we want to prove that the length of AA prime and BB prime and CC prime are the same. That's also not trivial. Because, of course, if I have started from an equilateral triangle, it becomes trivial. But no matter which triangle you start with, yes, then the point is that then these line segments become of the same size. And now I really don't know if they are going to pass through the same point. That is also something that my picture is so unprecise that I really don't know if they are going to pass through the same point. But what is your feeling? You think that they are concurrent as well? I don't know. We have to think about it. But my impression is probably yes.
Yes, I think so.
They also, and if that's a yes, what is so? Okay, so you probably should discover both of them. I don't know yet, so this is I'm not sure. But based on my intuition, probably that is correct. That if I draw these line segments, they are also concurrent. And then the focus of this problem is not proving concurrency, is proving that these line segments all are of the same size. Yes? So you can start working on this problem for the next week, and then of course I will continue my lesson, and I will try to manage the timing in a way that we pay attention. But what I expect you, if you go back and watch the videos, there are still some problems left. What I really expect, if you want to improve, of course you can listen and enjoy. That's also one part of the scenario. But sometimes I think if you want to progress, you have to work on the problem. So you have to manage your time. And I really want you, I don't know how many of you are following the algebra lectures. So I updated the Olympiad website yesterday for the third part. And that third part is a hard one. I have gone a little bit more advanced problems there, so in factoring polynomials. So be careful. The reason that I am just doing geometry here, because for the time being, I am sure that we have something for algebra. But algebra and geometry more or less have the same weight. So you have to have a knowledge on all of them. Okay? Okay, so I think that's a good point to stop here. Next time I will teach and probably solve some problems, yes? Yeah, that would be great if I can find time and design some problems for you, distribute them for you, and then you think, and then we come and discuss. Yeah. At the moment I cannot promise, but I will try to do my best. Thank you very much.